Now we'll talk about logistic regression for causal inference. So if you recall from our discussion about identification, we are trying to estimate this mean of this causal quantity, this potential outcome, which is the outcome that we would observe if everyone's treatment were set to little a. So if we treated everyone, what would the population average outcome be? And then we can compare that to what would happen if we treated no one. The problem is we don't know what the outcome would be if we treated everyone. We can only observe, in fact, the outcome that corresponds to the treatment that was actually given. However, under identifying assumptions, this quantity over here, which is what we want to know, is the same as this quantity here, which is the expected value of this function averaging over the observed covariates x. And so we need, if we want to approximate this is a population quantity. This is we just have a sample, so we have to go from causal world to a causal population to observable population, and then from observable population to sample, which is what we actually have. We need to estimate everything in here. So we approximate the expectation with this sample average, and we can approximate this function with regression. So we can do this. We've already seen how to do this with linear regression, which makes sense if the outcome is continuous. It's sensible to assume that it might be sensible to assume, I should say, that this regression function is linear. So linear regression, fine. But if the outcome is binary, like we saw, it's possible for that. If we estimate the conditional mean with linear regression, it's possible for that conditional mean to take values greater than 1 or less than 0, which doesn't really make sense if we know that this outcome has to be either a 0 or a 1 for everyone. So maybe it makes more sense to assume that the logistic model is correct. So practically, what do we do? Let's say that we have our data a, x, y, and in our data frame. We fit our logistic regression model. Here I call it M. And how do I get my estimate of the average treatment effect? How do I implement this kind of plug-in estimator? So all I need to do is I take my logistic regression and I change my data set so that I pretend that everyone was not treated. And essentially I'm just asking the logistic regression, what would have happened to all these people? What would have their probability of the outcome been, that's this P0, if everyone in my data set were not treated? According to this model, what would have happened? And then I just do the same thing. I ask the model what's the probability that everyone gets the outcome, assuming everyone were treated. I generate those two probabilities, and then I can take the average of those two. So that corresponds to this thing here, right? So the average of the conditional mean. Here the conditional mean is a probability, but that it doesn't really matter. And I can do any kind of contrast of those means that I want. So with binary data, oftentimes people are interested in risk ratios. There's no reason for that, really. I mean, it's just a question of whether you want to look at the difference of these counterfactual population means on an additive scale or on a multiplicative scale. So this is risk ratio. You could also look at risk difference. If you take the difference of those two, that's totally fine. You could also ask for about an odds ratio instead of a risk ratio, which is a little more complicated and I think needlessly complicated, if you ask me. But this is fine. And all of this can be done with the logistic regression, which is surprising to a lot of people, because a lot of people think that if you have logistic regression, the only kind of effect that you can estimate is an odds ratio, because they think, what I need to do is I need to take the coefficient for treatment and then exponentiate it, and that's an odds ratio. And that is an odds ratio, as we discussed, but it is not, in fact, the marginal odds ratio. So these two quantities are not even the same. So even though this is an odds ratio, it's actually not the one that you want that's kind of interpretable at a population level. And this is actually an area of some debate. So I pulled this off of Twitter. Believe it or not, people argue about, well, you probably know people argue about things on Twitter, but they argue about everything on Twitter, including statistics. And people get pretty mad about this. So, I'm in this discussion, I'm kind of this guy, because there's some people who, for reasons that I honestly cannot fathom, don't like risk differences, and they somehow think that odds ratios are more stable across different populations or something like that. Basically, there's debate, and I think hopefully you've understood in this course that the marginal odds ratio is more interpretable, and you don't even, there's no need to even go to odds ratios. Just look at risk differences or look at risk ratios, and you can calculate all this from your logistic regression as well. Just use the plug-in estimator, right? So therefore, this meme, right? Instead of thinking about coefficients, you just focus on the S-demand. You define it with potential outcomes. You just use the regression model to impute the two potential outcomes, and then you plug those in to the definition of the effect that you're interested in, and boom, done. Or you can be an idiot like this guy and just read the causal effect off of the regression table. So last meme, I promise. I'm once again asking that you please just use the plugin estimators. So if you're using a plugin estimator, you may ask, okay, how do I get inference then? Because if I've used the coefficient and exponentiated it, well, I can just look at the confidence interval for that coefficient and then exponentiate the bounds, and then that's the confidence interval for the thing I'm interested in. So how do I translate that to the plugin estimator? Well, other people have done it for you, so you don't have to worry about it. You can use the marginal effects package. It looks very similar to when we use this package as to use plugin for a linear regression. So it all looks the same. You tell it what your exposure variable is. You tell it that you want the robust standard error. And here, in the comparison, you tell it what effect that what the effect measure of interest is. So here, ratio average is the thing you type in if you want the risk ratio. But there's also arguments. You can look at the help function for this, and it'll show you that I think you can do odds ratio, risk difference, things like that as well. You just put a different input here. And then the last thing here is if you want your p-values, you have to say what is the null value for this hypothesis test. So here, since I'm looking at the risk ratio, if this mean and this mean are the same, then the risk ratio is 1. So that's the null effect that I'm interested in. Whereas for risk difference, if these two things are the same, that's the null effect I'm interested in, then the risk difference is 0. So the default argument for this hypothesis is 0. So if you're using a risk ratio or odds ratio, you want to set that to 1 so that your p-value reflects the appropriate null value for your effect estimate. All right, let's try it out. Here we have this data set that we've been working with a little bit. And I just want to use logistic regression to estimate the marginal odds ratio of treatment. And we would like to include age as a covariate. Let's copy paste all this in here. So all I need to do is change this so that I'm using the variables in here. Or alternatively, I could change the names of the variables so that they match what I have here, but let's do it the other way. So this is my exposure of interest, and then I want to adjust for age, I think it's just called age. And then the outcome is recurrence. Okay, that seems to have worked. Now we have that package. So here we need to change this to our exposure variable of interest. That's fine. This we want to be, I asked for odds ratio. So let's find out how to do that. Okay, so we have here difference, odds ratio. Yeah, how do we do odds ratio? This is, so this one seems right. So this, because I think this is odds ratio average. And this is log. So this gives us the log odds ratio, and then we just exponentiate that. Let's just make sure. It said there's a section about contrast somewhere down here. There we go. Yeah, so this is the odds ratio, the log odds ratio. So let's get that one, and yeah, let's do that. And this is correct. All right, here we go. So the estimate here is of the odds ratio is just a little less than 0, and we see the confidence interval. But this is for, okay, this is actually not correct because this is the log odds ratio. So if the odds ratio is 1, then the log of 1 is 0. So the actual hypothesis we should be testing against here is in fact 0. Is that right? Okay. That should have changed the p-value. Yeah, okay, good. So now we're getting the correct p-value. So it looks here like we have a pretty null result. The log odds is just a little bit less than 0, which corresponds to an odds ratio. So if you can exponentiate this. So for example, if you want the odds ratio, you could just do this. So this is our odds ratio, a little bit less than 1. And if you want confidence intervals on that, you can just take the exponent of each of these numbers as well. And this is still the p-value. Next problem here. Let's say you read a paper. It describes the analysis as a very large randomized trial. And they're reporting an unadjusted and an unadjusted analysis. The adjusted analysis is this just the exponentiated logistic regression coefficient. The unadjusted is like running a logistic regression without any covariance, which is equivalent to just like the plug-in estimator for the marginal odds ratio. And both are significant, but the adjusted result shows a larger effect size. And the question is, which, if either, can you interpret as a causal population level odds ratio? And why is there a discrepancy if the trial is so large? This one is pretty subtle. So the thing to notice here is that, okay, it's a randomized trial. So according to the identification results, we should be able to adjust for whatever we want, as long as it's pre-treatment stuff. And that should only be helping us gain efficiency, decrease the variance. It shouldn't be doing anything to the bias. So you may think, okay, we want to adjust. That's good. It's only going to decrease the variance, not change the bias. So both of these should be kind of going after the same thing. Also, the trial is so large, so the variance should be very low in either case anyways, and you should kind of be getting the same result. So what's going on here? Well, the issue is that this adjusted analysis is not actually is not estimating the population level odds ratio. So it's this, right? This thing is not the same as this. So if they had used a plug-in estimator with logistic regression, then you would get basically the same answer, and the adjusted version would just be more efficient. Great. Smaller variance, smaller confidence intervals. But because they're basically comparing apples and oranges here, so the unadjusted odds ratio is reflective of the population causal odds ratio. That's really the thing that they're interested in. The exponentiated logistic regression coefficient is, again, this like conditional odds ratio under the assumption that the conditional odds ratio is constant across the population. So it has a much more convoluted interpretation, which is not usually what people actually want. And so, of course, those two numbers can just be different numbers. There's no reason they have to be the same. This one is not what you think it is. This one is what you think it is. It's a very large trial, so there's very little variability. Anyway, so here actually if this is the choice given, I would look at the unadjusted estimate. Of course, we could do better than either of these. We can do the plugin with the logistic regression and then get something that is a population level odds ratio. It's causal because it's randomized trial, so the identifying assumptions hold and everything is good. All right. So now let's talk about in this example here was a randomized trial. What happens in an observational study where you don't have the randomization? And let's assume, however, that you do have you have measured all the right confounders. Okay, so the identification result holds. We're okay because we basically have randomization within each subpopulation. But what happens if the actual relationship between the covariates and the exposure is not aligned with the logistic regression assumptions? So here we have a setup. This is a data generating process that I made up, and here the conditional the probability of getting the outcome as a function of what treatment you get and your covariates varies. This is basically the log odds of the outcome is linear. So that lines up with what the logistic regression model is. And if I simulate data like this, here I can calculate the true risk ratio because I can look at the potential outcomes. And this is the true causal risk ratio. If I do an analysis here, I can generate one data set with 2,000 people in it, so I don't get to see the potential outcomes in that data. I can fit a logistic regression. I can construct my prediction function with logistic regression. I can predict for everyone what would have happened if they were not treated, what would have happened if they are treated. So these are predicted probabilities. I can take, you should see this reflects very closely. This is just the plugin estimator based on these logistic regression probabilities instead of the population outcomes. And then we construct this estimate, and you can see it's very close. So that's great. So it works. And in fact, if we repeat this many, many times, you can look at the sampling distribution of the plugin estimate, and you see that on average, we're getting the right answer. So this is an unbiased estimator. Of course, there's some variability, but it is unbiased. Now, what happens if the model is misspecified? So here, the probability of getting the outcome no longer varies. The log odds of getting the outcome no longer varies linearly with the treatment and covariates, but now I've introduced this square term. So the log odds, actually the relationship between the log odds and the covariate is some kind of parabola. Or more generally, any other kind of nonlinear function would give you a similar result. So here I'm using this parabola. In the analysis, I'm doing the same logistic regression. So I'm fitting the GLM regressing y onto a plus x. And if you recall it, the assumption here is that this is a linear relationship. So even though these data are not, it's not going to be a great fit, we're just going to kind of find the best S-shaped curve that fits that data, and then use that as our plugin estimate. So we do this. This is the same here, but now we see the answer is much bigger than what it actually should be. And if you look at the sampling distribution, if you repeat that process many, many times, you're going to see that we're actually biased, heavily biased. We're saying there's a much larger effect when really the effect is, more moderate than what it appears to be according to our analysis. So that's bad. Okay, that's quite bad. And the problem is this: so we have the identification result in this simulation. Clearly, if you draw a DAG here, y0 and a are independent given x, because we just have x going into a, x going into y0. There's nothing else that goes into both a and y0, so these two are independent given x. So we have the identification, so this step works. The problem is that we're doing a shitty job of estimating this conditional mean, because this conditional mean the log odds of that is not actually linear, but then when we do our logistic regression, we're assuming that it's linear, and so we're kind of trying to slap a line over some nonlinear relationship. And of course, that means that the predicted probabilities are not accurate. So that can happen. And in fact, that's very often the case, right? Why should we assume that this particular kind of linear relationship holds? In reality, things are often nonlinear. Thankfully, there is a special exception to this, which is if there is randomized treatment. And we saw this also for linear regression, where the linear regression plugin estimator is biased in general if the true relationship between the covariates and the outcome is not linear. Now we're going to have bias when we're trying to estimate these causal effects. But we saw there's a special case, which is if the treatment is randomized, it doesn't matter if we've misspecified the model and said it's linear when really it's not. It actually doesn't matter. And the same thing happens for logistic regression. So if the treatment is randomized, you can still use logistic regression, even if the model is arbitrarily wrong. And the reason for that is because if it's randomized, you actually don't need to adjust for anything anyways. You can get an unbiased effect by adjusting for nothing. And so the adjustment here is kind of only helping you soak up some variance. Again, as long as you're adjusting for pre-treatment stuff. So here's the kind of empirical proof. I have this same setup where I have a nonlinear relationship between the covariates and the log odds of the outcome. This is the true risk ratio. If I do my analysis, repeat it many times, I see it's unbiased, and I'm getting in general the right answer, even though in my regression model I'm not including this square term, which I should if I wanted to actually capture the relationship. So coming off of that, intuition about variable selection also holds for the logistic regression plugin. So we talked about this stuff in the context of linear regression. What are the variables that you want to include in your model to adjust for to get causal effects? And it's the same for logistic regression. So you never want to include things that are colliders, and this includes mediators are effectively colliders in the causal world, which we talked about a bit last lecture. So anything that's after the treatment, you don't want to include. Things that are before the treatment, if it's an important confounder, something that affects both the choice of treatment and the outcome, then that should definitely be included. You definitely want to include stuff that is only affecting the outcome, even if it doesn't affect the treatment, because that's going to actually reduce the variance of your effect estimate. And you should consider maybe not including things if you know a priori that they are only affecting the treatment, but not really affecting the outcome. Of course, all of this is not stuff that you can actually know for a fact or not, but you have to reason about on the basis of your intuition and domain knowledge and prior studies. These are not things that you can test, at least not the relationship with the potential outcome, because you don't observe the potential outcomes usually. So a couple more problems here. Let's consider this data generating process. So a couple things we need to do. One, compute the true causal risk ratio. Two is generate a large data set and estimate the risk ratio from these data using a plug-in estimator with logistic regression, but also a plug-in estimator using linear regression. Because recall, just because the data are binary doesn't mean that we can't estimate the conditional mean with linear regression. It just means that estimate might be a little janky, or it might go outside the bounds, or something like that. But you can do it. And then we compare those two. So let's have a look. Well, try it yourself, but I actually already coded this one up. Okay, so here is our data generating process. I modified it a little bit. So in the question, I didn't have these, but I added them in, and it's the same thing. So this one is just what happens if A is 0. Then I'm basically I can read off the potential outcomes, even though this data generating process is the observed data generating process. I can read off the potential outcomes by saying what would this probability be in here if I fixed A to be 1? What would it be if I fixed A to be 0? And so that gives me the two true conditional mean functions of the potential outcomes, which I've gotten here. And then I generate Y by flipping a coin. If A is 1, I flip a coin with this probability. If A is 0, I flip a coin with that probability. So this is the same. The reason for doing it this way is that now I can generate the causal effect, the true causal effect, by taking a really, really large number of samples from this distribution, and then taking the mean of mu1 and dividing it by the mean of mu0. So this is it gives me an error because I did something wrong. Okay. Okay, better. So the true risk ratio here is about 2.2. True causal risk ratio. Now let's do an analysis. Let's draw a data set, 500 samples in this data set, and let's fit two models. One is the logistic regression model with this covariate X and the exposure A as predictors, and the other one is the linear regression model. And if you remember last time, we could see what these functions look like in a similar setting. So maybe we can actually do that here. Let's do say X, and then maybe like this. So I'm going to do the predictions from the first model. Yeah. There we go. Okay. So this logistic regression model, since this is a binary variable, it's essentially one curve for a equals 1 and another curve for a equals 0. So that's what we're seeing here. These are the two predictions. And then for the linear regression, we're going to get something very similar. Looks like that. So here it looks, for the logistic regression, these conditional means as a function of X, they look pretty linear, but they're actually not. So these are actually parts of the S curve. It's just the S part is way up here on the right. And you can see that they actually have different slopes because the two curves are shifted by different amounts. Basically, the shifts correspond to the coefficient on A. Because that you can think of that as like kind of going into the intercept if A equals 1 or if A equals 0. So that's why this looks like that. Okay, so those are our predictions, and let's use the marginal effects package now, and we can estimate for the logistic regression model. Let's calculate the risk ratio. Yeah, all of that is good. So this is the answer we got. By the way, when you output this, so let's look at what this is. I can save this, right? And then this is like some kind of table. So I can do result estimate. And that just gives you, this is the estimated risk ratio. So here, let's just try to print that out. Let's forget about the inference and all that. So this is for logistic regression. And then for the linear regression, let's see what the estimate is. 2.3 versus 2.4. And then let's recall what the truth was. Truth is 2.1. So this is actually closer to this than this is. And in fact, let's make the data set really big here. So the observed data. So basically we have the population. Let's do the same thing. So let's get for logistic regression, for linear regression, and then the truth is what? What was it again? So which of these is closer? Clearly this one. This is the linear regression estimate. This is the risk ratio that I estimated from the linear regression plugin. This is the risk ratio that I estimated from the logistic regression plugin. This one is closer. Okay, so again, I'm just trying to break the association in your head between binary data, logistic regression, continuous data, linear regression. Because in fact, I can estimate a risk ratio using a linear regression, and I can use linear regression for binary data, no problem. Is it always the better choice? No, not at all. Not at all. That's not what I'm saying. But so why is it that the linear regression plugin is giving us the right answer here, and the logistic regression plugin is too big? The answer that we're getting is too big. It's precisely because of what we're seeing is this kind of model misspecification bias. If you look at this data generating process, look at the probability. The probability that y takes the value 1 is a linear function of x and a, not a logistic of a linear function, because these outputs are already between 0 and 1. Because here x is binary. Well, then what are my plots? Hold on. Why is this? Hold on, I confused myself here. I'm confused about these plots. Oh, of course. Okay. So yeah. So it's just an artifact because I used a line here, but there really are only predictions at 0 and 1, because x actually only takes values 0, 0, and 1. So these are the predicted probabilities here. Sorry, that plot was a bit misleading. But the point is that the covariate is binary, the treatment is binary, and here this function, if x is 1, this is 0.3, if a is 1, is 0.3 plus 1, 0.9. If these things are 0, then we get 0.1. So I could get 0.1, or I could get 0.4, or I could get 0.9, basically. Those are the different combinations. And it's always between 0 and 1, and it's additive. So it actually is a linear function of x and a, the probability. And so the linear regression plugin is unbiased because that is the correct model. This is actually modeled, this is captured by a linear regression. This is not captured by a logistic function of a linear regression. So it's not the log. If I had here p logis of this, then the logistic regression would be doing better because it would be making the correct assumption about how the data are generated. But without this, the linear regression is actually making the correct assumption. If I had here, however, I don't know, some other, well, actually here they're binary, so there's maybe like an interaction term, right? If I had x times a or something like that, then neither of those plugins would be unbiased because they're both not including this this interaction term. So the point that I'm trying to make is that the bias of your estimator just depends on you having captured the correct form for the data generating process, or closely approximating it in some way. And the way to closely approximate it is not necessarily to use logistic regression or necessarily to use linear regression. Is to just think about what the relationships are. And in general, that's actually really hard to do, right? You don't really know what this should look like. You don't know if it's going to be linear in the log odds, or if it's going to be linear in the probabilities, or if it's nonlinear, or what the heck is going on. And there's no reason that you should have to really think about this. And so next lecture, we're going to talk about basically ways to do regression where you don't have to make assumptions about what that function looks like. Or rather, those assumptions are much weaker or more flexible than saying specifically something is linear or something is not linear, or I have this interaction term or I don't, or I have this square or not. So that's the entire point of non-parametric regression, because it's very silly to assume that you know these things, and it's very hard to reason about whether they should or should not be true without having a lot of data, right? So that's that problem. Now let's do this one. This is actually the same problem that we did before. We have this RCT data, and the question is, for these data, you see I adjusted for age as a covariate here in the analysis that we did before. The question is, do we have to worry about model misspecification? Because we just saw here that in this case, the true data generating process was not linear in the odds of the outcome, and that meant that the logistic regression was biased. So do I have to worry about that here? And the answer is no, you don't. because this is the special case. This is the special case because if treatment is randomized, the model misspecification doesn't matter because you don't even need to be adjusting anyways. But adjustments just benefits you, right? And so that is the answer to the second question here. Can we hurt our estimate by adjusting for more pretreatment variables? Generally, no. So in a randomized trial, since the A is randomized, there's no instrument and there's no confounder, right? Nothing is an error going into A. So every variable is just an explainer. And typically, adjusting for them will improve your precision. If you have large enough data, anything will improve your precision. It might be just a little bit, but you definitely want to include things that have strong relationships with the outcome. That will improve your variance and give you smaller confidence intervals. Other things might not help too much. In theory, they all help with large enough data, but in practice, you really want to focus on things that you know have a strong relationship with your outcome. So to summarize this lecture about logistic regression, first off, what is logistic regression? It's the same as linear regression. We're just searching a different set of functions. And minor point also, we're using a different way of grading what we mean by good or bad for those functions. But the goal is the same. The goal is still to estimate a conditional mean. So it really doesn't have to do with as much with the type of data as it has to do with what is the set of functions that we're searching over. Second point, interpreting coefficients, it's usually nonsense. We saw this was the case for linear regression. It's even more the case for logistic regression. Third point here, you can use logistic regression for prediction. And this is very simple. It's very much mimics the case for linear regression. You have to, ideally you're using a separate test set to evaluate your prediction. And the only kind of statistics problem here is how good is my prediction really and how can I tell? So use a separate test set. And the way in which you measure what you mean by good prediction should be determined by what it is that you're trying to do with that prediction model. And again, that's not a statistics problem. That's a kind of domain problem. Are you using this in a setting where the treatment is very expensive and we want to make sure that the people who it's being given to really need it? Or are you just trying to catch all the possible cases? Those are basically the usual trade-offs. Lastly, you can use logistic regression with robust standard errors, ideally, as a plug-in estimator for causal inference. So the marginal effects package automatically translates all of the confidence intervals on the coefficients, those robust confidence intervals, and mathematically translates those to confidence intervals and standard errors on the plug-in estimate, which is what you actually care about. So you can do that. Things that you need to be aware of is that the logistic regression, if it's misspecified in an observational study, so the relationship between the outcomes and the covariates is not captured well by the logistic regression, then that's going to induce bias in your estimate of the causal effect, even if you've measured all the confounders. So there's two places you can go wrong. You can not measure the appropriate confounders, and then you can also just not use the right model. Either of those will kind of screw you over. And in terms of selecting what confounders you're going to include, that has to be done, like in a linear regression setting, using domain knowledge to select the appropriate pre-treatment adjustment variables and never adjust for things that are post-treatment. Well, that's it for this time. And next time, like I said, we will start talking about non-parametric regression because it really sucks that you can get screwed over two different ways, right? Even if you go gather all your covariates and you've thought carefully about this, you can get screwed over by not doing a good job estimating this conditional mean. So let's introduce some methods that do a better job at estimating these functions kind of no matter what they look like, and will be robust to different kinds of model misspecification. You don't have to manually say something is linear or not linear or whatnot. It'll just figure it out for you. And that will also be better for prediction, because when you're doing these predictions, you'll just get better predictions. You get better fits. So here we had a logistic regression in this prediction setup where we saw that the predicted probability for somebody who didn't have the outcome was actually higher than for somebody who did go on to have the outcome. But if you're fitting these curves more accurately, then these predicted probabilities will be closer to the truth. So it'll help for that. We'll also see that for description, it helps in a sense because it keeps you from doing stupid things. because these functions will not end up having any coefficients that you can typically interpret. And that's actually a good thing, because then it saves you the trouble of having to try, because at the end of the day, they're not really interpretable. So that's for next time. I'll see you then.